Sorry, Space Centre.
We'll let you press on and catch up on time, yeah?
Right, yes, I'll try and keep everyone, or try and get us back on time. I've got 35 minutes. I can bring it down as quick as we can. If we need to, I can talk faster. I'll obviously judge, depending on people's faces, how successful that is. So what the presentation that I really wanted to give you, I guess I've sort of given presentations at AMSAT now for quite a few years, and it's really just to sort of give people an update of what really sort of we're progressing on. So you've seen some of the stuff that we've had some of our summer students working on with undergraduates, but really what I wanted to talk to you about some of the next things, and in particular what we're doing with Strand 2 and supporting some of our future missions, as well as some of the more recent work which I've been involved in, which is the UK CubeSat Forum and the Bring Your Own Boards Day. So last year what we did is we actually talked about some of the results we did out of a Phase A study, came out of the NSTP programme funded by the UK Space Agency, TSB Collective. And what we were actually doing with that is we were then looking at identifying, having two CubeSats that would come out of deployers, where they would then, during some sort of approximate days of commissioning, we'll be able to then drift apart in the orders of kilometres, after which we would then want to then try and use our propulsion systems to bring them back together and to dock. Okay, and what we've been doing previously before that is to figure out how we would make that happen. Okay, so there's lots of things that need to go on in these particular systems, precise deployment, some of the things that in fact Torsten's talked about with QB50 and the sort of work and how you would deploy these things to not just keep them together in my case, but also to stop them from colliding with each other. As well as then the technology that would need to go to make sure that you can do relative navigation between the units, as well as positioning between them. And in particular, the piece that sort of got the headline is this COTS infrared LiDAR, which you all may know to be commonly known as sort of the Kinect sort of thing. So the things that you have in your home that your kids just do this and this in front of each other for literally hours on end, and they've obviously got the energy to do that. And so with that in mind, we've obviously been sort of working down sort of this sort of side where you're looking at sort of research sort of feasibility, and we really want to sort of push this sort of up into the technology demonstration domain. So why would we actually want to do this? The reason why we would want to do this is because to build up new structures in space is particularly important. Okay? The reason why we have the International Space Station is where it is has required massive collaboration between these different types of systems. And the LiDAR system, in fact, that they use for the ISS is on the order of $500,000 US. So with that in mind, what could we do to take a commercial shelf LiDAR system, which actually has two really, really good pieces of technology inside them, one of which being a diffusion grating to scatter a laser in many, many different directions, and then a system on chip, a specially designed ASIC, to then figure out how to then interpret that technology. And it's about those two technologies in combination which has sort of driven down the cost of modern gaming systems that we know and use today. And if we can sort of build these satellites together, then what we can actually do is then put together different structures. Okay, we can create different types of mirror systems. We can create telescopes. We can build new sort of systems. And it's that sort of Lego type mentality that we're looking to explore to be used in space. And obviously the CubeSats are a wonderful thing. They go up potentially as sort of quads, 8s, or whatever number we want to use. But in that particular instance, we might want to think about how we would then use them together collaboratively, either as a network, or perhaps if they can dock together, then why not use them collectively to share what they have. Now, the Strand 2 previously, what we talked about was actually having a set of sort of core avionics with actually having some butane systems here, and you can see the different sort of thrusters that we would use on the particular system. And what we would then have is have some sort of LiDAR system and docking system in here. So we need to be able to have a docking port, which is a 3-pronged port there, as well as some imaging systems, optical and LiDAR. And we can use some of the existing Strand 1 avionics, which is now flown on QB50 1 and 2 as well, including regular COTS systems. So we've got, to not necessarily think about the technologies that we need to fly. It's that make or buy sort of decision making that we all have to do our trade-offs on. But in particular, we want to sort of explore some of the new features, really carbon fibre structures. Okay, can we do something better with our particular structures? Increased tank size and thrusting capabilities. Again, we'll have to. We're already looking at this, and to start thinking about close proximity operations and the actual application of doing these things and being able to move around each other and to be able to operate in very close proximity. Now, there are missions that do already do this. Okay, there's a mission called Prisma, which is done by the Swedish Space Corps, the other SSC, and they have actually been able to do this, not necessarily with a LiDAR, but with an optical system, and they've been able to get their satellite go around in what we call 2-to-1 ellipses, and the Prisma system will essentially be going around sort of in an orbit, and they essentially go around very, very close together, and they will go anywhere down to about 14 meters they've had them down to. But typically they have a safe zone, which is at about 60 to 80 meters. They had 4 different types of propulsion systems on those things that they were testing, and they were sort of microsats. One was 150 kilos, the other one was about 60 to 80 kilograms. So you had a chaser type one, and then you had one that was essentially passive. But what they did is they kind of cheated, and what I mean by cheated is that they were a cooperative target. Okay, one of the things that we would want to do on in any spacecraft design is don't make assumptions. Okay. As soon as you start making some assumptions in these sort of things, especially when you're doing risky maneuvers, it's not something that would necessarily be advised. You need to have your own visual inspection system as well, not just to be guided fully by perhaps differential phase GPS. And of course we want to have docking mechanism and then perhaps some room for some further experiments. So last time I talked to you about how we were then testing the Microsoft Kinect actually in space, and you can see the sort of Microsoft Kinect there. This is it sort of stripped down. That was going into one of our Hermes thermal vacuum chambers here. And we were looking to use this for Strand 2 and a new program which is called Arrest. Now, Arrest is a program which is done with Caltech as well as NASA JPL, and in that particular instance they're looking to build the deformable mirrors. So it's the mirror part, the actual payload part of this particular satellite that they would want to be developing, and we would then be working on actually the platform and the subsystems. And the other application that we had was one called InspectorSat, which is actually together with was Astrium, beg your pardon, now Airbus, and some of our Russian colleagues that we worked with. And they were wondering whether or not we could actually use this technology to look and inspect solar sail unfurling. So we had some really great images for those of you that know the Japanese mission Icarus, okay, and they had video and they showed it sort of going across. And what was really interesting about that is actually they had specular points where as the imager sort of went through, it kind of just went bright, and you essentially saturated your imager. And when you do that, it's very, very hard for you to then get a fix of your relative range and pose. If you're doing it purely optical, it's very, very hard. And the problem with that is that, as with every sail, it billows. All sails billow, whether or not you like to think it or not, in any direction. Okay, it was based on the force that you apply to it. And that particular shape isn't actually a parabola, it's something called a catenary, which is actually what happens when you have a couple of posts and you swing a chain through it. That's the name of the shape that it creates. And it's a Koch function. And we were looking to model that and see whether or not we could put all these systems actually onto some embedded platforms. And we looked at sort of embedded arms, Smart Fusion 2 FPGAs, but also more classical sort of Leon 3 vertex systems that we would find at ESA. So one of the things that we went around to do was actually to then model and simulate the actual sail itself. So this is a synthetic image of the sort of image you would get at a range of 1 kilometre with a 5-degree field of view camera, imaging a sort of worst case sort of system when you're looking at a sail. Now what's really important about this is really how it's folded and how it's put together. Okay, from this particular sort of sail, you can actually perhaps tell something about its shape. You can look at the specular points and perhaps know where there are focal points, and if there are any deformities on the sail. It's those sort of features that they're looking to get back and try to sort of push the sort of edge of the state of the art. I know this is something slightly different, but here you can actually see all of the different sort of effects that it would be, and of all those creasings and all those things we would want to know. Now if you turn this thing slightly edge on, what you actually then start to see is you kind of see all these edges. You can still see all the edges, okay? But for a third of this orbit, it's going to be completely black. You're not going to see anything. Then there'll be another third of the orbit where you're practically staring at the sun. Okay? And then there'll be another third of orbit where it's essentially going to be flat on like that, and then slowly but surely it will go like that, and you'll get this big flash, and then it's gone again. Okay? And we then have to do all of the imaging and all of our visual inspection that we need to do on those particular things. Now that's very, very difficult to do optically, also very, very hard to do even with a LiDAR system. And the reason for that is that these are highly specular surfaces. Very highly specular surfaces. So what we've been doing is we've been doing experiments actually in one of the gymnasiums. at the university, and you can kind of see what this is here. This is actually the shape of the sail. It's actually laying flat here, but even on the side, we get a huge specular reflection. Now, just even looking at that image, you're not going to tell me what sort of shape that is. Is it a square? Is it a triangle? Is it a star shape? Pick your shape. You know, you wouldn't be able to tell from that sort of angle, and that's the sort of thing that we're going to see. But we can see here, just from the reflections of the actual patterns that we can see on the wall, that actually the light simulations that we've been doing actually make sense. We built our own ray tracing systems that we had then operate on the systems, but we've been able to do that and start to sort of push this along. And the reasons why we want to do this is that this is useless to us and can potentially be very, very harmful to our actual images. So this here is a 1 meter sail that is actually square. You would never know it. But as soon as we sort of scale that up, okay, to a 25 meter sail.
Shadow.
Yep.
Shadow.
Oh yeah, you can see it from the shadow. Yeah. You're not going to get a shadow in space, though, are you? So we actually had a huge halogen lamp, that a 2 kilowatt halogen lamp that was suspended right on the ceiling. But yeah, right, there is a shadow in this particular image. But just from that image in the middle there, you wouldn't know. And the reason why we would want to do this is to actually prevent our images from getting burnt out. Okay, as soon as we start scaling things up to 25 square meters, you're then essentially going to be pumping kilowatts of energy potentially into a very, very small point. Okay, and because it is specular, we don't want to go through those danger regions where if all the light rays are all coming to sort of one rough region of space, if we fly through that, it's goodbye Miami for that particular sensor. Okay, you're going to be dumping kilowatts into an imager that it won't be able to take. So, of course, one of the things that we actually had is we had that wonderful BBC article that really was sort of showing how we were pushing this forward again and using the sort of same thing of, you know, let's see what we can do with the worst case COTS on a budget of 0. But unfortunately, out of the blue, NASA went, we're going to pump 13.5 million into it, which put a bit of a downer on it, if I'm honest. But in this particular instance, they've been looking at demonstrating rendezvous and mechanical docking, small spacecraft in orbit, proximity operations, as well as a COTS LiDAR. If you actually read the full blurb, that sounds a bit familiar, doesn't it? And if we actually look at the dates between this one and this one, it's about 10 days. Okay, so that's the sort of difference you're going to get. So previously, what we'd been looking at is we'd actually been looking at the raw imagery itself. Okay, now this is our CubeSat sort of speckle image. This is what you're going to get out essentially of a raw Kinect as soon as you start hacking into it at the software level. But you can see these huge specular points that are going to come off. You're not going to see it, and then all of a sudden it's going to be right there in front of you, as you can see there, those little sort of white flashes. So that is us swinging essentially a CubeSat on a bit of string as it's coming towards us on an imager at a known rate and velocity. And what's really good about these sort of images is you can actually start to see what it looks like, okay, under different systems. You can look at the materials on here. You can start to look at the particular surfaces. Are there any particular things that maybe you want to have? And in our particular instance, what we've actually done is fitted it with actual omnidirectional reflectors, infrared reflectors. So we have these small ball-type things that we can fit to the side, and then we can create patterns on the side, and we can look for those particular patterns. And what we can do is we can then measure those, and we can understand their range, their pose, and from that disseminate then how far away it is and on what orientation it is with respect to us that we're imaging from. Now, what I will try and do is show you actually one of the things that we've been working on, which is trying to push this on a bit more. What we needed is we needed a platform to demonstrate how this system worked. Now, this particular system you will have seen, for those of you that went to the Bring Your Own Boards Day, is our Granite Table. This is an ultra-flat Granite Table, which we actually have these sort of systems. You can see here robot systems. Instead of having a cushion of air typically blowing up like on a hockey table, we're blowing it down through these pads. And so any torques, any part that we want to have on these particular systems will just essentially recreate that same sort of motion. Okay? And what we've been able to do then is sort of expand on this. Obviously, we've got a weight on the top for whatever payload we're using, but at least this is really ultra flat, and it's got dampeners on the feet, so it's really reliable without any vibration. Now, what this is all going towards is a package configuration for a rest, which is our sort of final sort of end game after Strand 2, where we will actually have some deformable mirrors here. This arm will expand all the way out here, but you can kind of see roughly what it looks like as a sort of model here. You have the mirrors here, and then you have these sort of craft. We have a central middle CubeSat, which acts as our sort of main interface point, and some of these ones can essentially dock and undock and move around. And if we move around to a certain size, we can change the focal lengths and the resolutions actually of our telescopes and of our images. Okay? So in this particular instance, these reflectors here would reflect up onto the arm, and the arm then has the actual connector there, the actual collector that we would then use for the light. So what have we been doing sort of to push that forward? Hopefully you can hear this. I don't know if there's where the audio cable's gone. But what you should be able to hear is you should be able to hear the thrusters flying. So there's thrusters firing on this particular system here. And this is our system that you hope, for those of you that went to the Bring Your Own Boards Day, will have seen. And here you can kind of see our target down here. So we're actually starting to now push the use of COTS LiDAR all onto the platform. Again, this is just an Amazon box that roughly is the rough shape. And in this particular instance, what we're interested in is making sure that we can get all that working on an embedded environment. This is a great project that we've been working on. Now, I've been looking at sort of hacking these sort of tools for quite a long time, and we've had an MSc student called Richard Duke who's been bringing these pieces all together. Now, we've got a 20,000 milliampere hour battery, which is roughly 100 watt hours by calculation. We use a Raspberry Pi processor, a COTS LiDAR, which is actually fits all in a 10 centimeter system, and actually draws about an amp. So when we want to use this, we can connect it over. Now, what this particular system does is it takes the LiDAR images and it gets the detection going, and we then compress the image. It goes over a Wi-Fi dongle, and then we plot it on the screen. That's essentially what you're seeing here. But there are some stages in between that to bring this thing down. This particular system operates at about 8 to 10, push 11 hertz. Okay. Now, what would be really ideal is actually we would just want to calculate what we would call the state vector, and the state vector is how an object is moving in relation to us. So it's its position, its velocity, potentially the quaternion rates, or roll pitch yaw with respect to us. And then after this, we would want to then do closed loop control. Now, there's a guy with a keyboard that's just going firing thrusters in this particular instance. But what we would want to do is sort of change that so that it's actually closed loop control, that it can then move around it all on its own, figure out where the docking port is and then go in for it, and do all that in a fuel optimal way. So that's the sort of system that we're looking to then implement. So that's kind of what we've been doing myself in the group that I've been working on, is trying to push all this technology along. Now, we've been doing a lot of work with software-defined radio as well, but there's literally not enough time to talk about that. We would need many, many moons to be able to talk about that. But what I want to bring your attention is the UK CubeSat Forum, which is a fairly new entity, which is actually the bringing together of academia, industry, entrepreneurs and enthusiasts such as yourselves to really bring out the CubeSats for everyone mentality in the UK. And now this is primarily almost as a lobbying tool that we can all potentially use so that we can get our views across, certainly to government and those that actually hold budgets and hold the keys to us working together in the UK. And this is particularly important because CubeSats, have commercial purposes, but they also have purposes within education, and they also have purposes within people that are just interested in doing it, or even starting up new businesses or applications. So that's sort of the forum itself, and we actually have a website that you can go in and look up. We've got now 122 members that range from, let's see now, people from ESA all the way to directors in Astrium, all the way through to people like myself or Joe Blogs on the street who's just vaguely interested and heard about CubeSats. And you can actually go on there and search who's on there and figure out if there's anyone that's of interest to you that's interested in ground stations. Now, for those of you who didn't go to the Bring Your Own Boards Day, you're in for a treat. You're in for a treat. So what we actually did in the last year is we decided to bring together a day of people, and in fact it was created by myself and Wouter, I think Graham, and maybe Steve Greenland was there as well, and we said, do you know what, why don't we just get together with all of the kit that we've got and we just actually talk about it. Okay, you kind of leave all the stuff that you would typically have at the sort of front door and really get into the nitty gritty. So for those of you that wear ESD straps for all the day, let's get down and dirty and talking about these sort of things. So instead of BYOB, bring your own bottle, booze, bombs, whichever area of the globe you live in, you can actually then bring your own boards. And we actually had a real fantastic selection of things yesterday. We actually had FPGAs and RF systems, in fact, by Mr. Mark Bauer, who's there in the red T-shirt. Hold it. Wait for everyone, Mark. Please go and talk to him if you're interested in SDR and FPGAs, as well as my PhD student there who's working on similar sort of technologies, in fact, with the same Z board, Mamatha, who's at the back there. We then had ISIS's equipment, their OBCs and their COM systems, demonstrating those new ones. We then had Open University's imager and camera, as well as then what this is a picture actually of me, but what it would look like after the CubeSat itself had been to Jupiter and back after about 12 years of radiation. Obviously, most of the imager is fully burnt out with the effects of radiation. That's not all. We actually had then the QB50 stack that we discussed previously, which has then got the sensors on it, the magnetalkers, the magnetometers that are flying on QB50, as well then as the Clyde Space, as well as the catapults sort of flat sat system that they've got here. So it has all sorts of transceivers, batteries, and computers and things on here. So this was a fantastic day where we all got together, really just to nerd out over hardware. In fact, in the same way that you do just outside there. So instead of that, this is more on some of the equipment. And so we had talks, very, very short 10-minute talks from everyone, as well as we had lunch where people really just could a chance to get down and chat. So rather than it being less sort of formal, it's a chance for everyone to sort of get together and really just have fun with the equipment that they know and love. We also then had a good pass with Graham and as well as Vasser and a lot of other people there, getting out our antennas, picking up FunCube on a glorious day out by the University Lake. And Graham, how many packages you get? 60 something? 60 something, and it's got a small number on the other ones. But you can actually see one of the things is get out there, do what we like doing best, which is really kind of important. So I'm trying to bring us back on time. I'm sure you will have actually got questions. But really, I wanted to leave it at that, and that's really just to give you a flavour of the sort of thing that we're doing without actually then starting to impose too much technology with the SDR stuff. Yes, be happy to take questions.
Any questions? No, surely. No, I'm surprised. Yeah. Nobody on the internet? Nope.
People usually have quite a lot. Processing. What do you want to know? I mean, so.
Please talk next year.
Focus more on SDR because the horizon there is just tremendous. It's.
So how many people know VHDL in this room? Oh, I'll give people perhaps less credit than they're actually due. So if I was to do stuff on VHDL and multi-core systems and those sort of systems, people would genuinely be interested in that. Yeah? All right. Next year, we'll do it. We wouldn't have been able to fit it in half an hour, though, today. No.
Yeah, we're within time. Any other questions before...
Chris, I understand you've been doing some work with GNU Radio. What sort of success have you had at higher bit rates on that?
So we have had recordings are at 38K4 and 1 meg on S-band, which has been brought down. I've had quite good success. That's probably all I should say, I think.
No more.
GNU Radio can work very well, but not with short bursts of data. We would need to use our own systems. I think you'd have to use something a bit more custom. If it's sort of short bursts of data, it doesn't have really the time to lock on, and people's computers are just too different. You wouldn't be able to just release something vanilla that everyone could just use. I actually don't think that would work.
On that front, I think I've got half a clue as to where that problem might be. There always seems to be something left stuck in the buffers in GNU Radio from the previous cycle round. And so you need to give it long enough to clear that, and then it will decode fine, is my experience.
So you'd have to edit this. So what GNU Radio is essentially a set of libraries that are written in C, C++, that is then joined together with Python with a graphical interface. Now, what's particularly interesting about that is that it does allow you to essentially do sort of blocks of things, like, oh, I'll have a filter here, I'll have a demodulator here, we need some gain here, we need to change the phase of this particular thing and recover timing here. But you're relying on other people's interpretations of things. And that's really where the problem comes in. So, for instance, even with systems like Multimon, the things that we use day in, day out for using these systems, I found 2 major bugs in literally the last 2 weeks. 2 biggies as well, on fairly regular demodulation stuff. And it's just whether or not I actually have the time to go through all this code. So I'm a lecturer, I have to teach as well as help build a ZAO, and then work on Strand 2 and the rest, and QB50, and do all these other things. But yeah, I mean, there are certain blocks that I'm sure we can make work.
Certainly on the PSK side.
Okay, I think that's it with tea break now, but big thanks to Dr. Chris Bridges, if I give him his full title, and to his team members and colleagues, many of you have seen wandering around as well as part of it. So big thank you. Always nice to see you here. Very interesting to hear all the work that's going on.